we're looking at problems where it asks us to find some kind of a torque, or we're finding net torque. Okay, so starting out, if we're just thinking of the concept of net torque, well, torque in general is force times a radius. So if we didn't have anything right here, we can understand that this pencil, in this example, that pencil would tip this way. So these are just pennies on the end of a pencil. Pretty basic idea using things you can find anywhere. But we have a penny here, and we have a penny here, and that produces a balanced system. Okay, so our net torque in this type of problem would be 0. The torque exerted by that penny is going to be equal to the torque exerted by that penny. So if we want to find net torque, then we have to find torque on the left and then torque on the right. Okay, so our equation for torque, let's just write that down off to the side. So torque is force times a radius, and there's also a modification to that equation if we have an angle. So if we have like a crescent wrench or something like that, we're pushing at an angle, it's going to be force times radius times sine of theta. Okay, so whatever angle we're pushing on the object, that's where that comes into play. So it's force times radius times sine theta, because that sine component will reduce that force that I'm pushing with. Okay, so I have a couple examples below. Let's check them out, see if we can figure them out. So for example 1, 2 people are pulling on ropes wrapped around the edge of a large wheel. The wheel has a mass of 12 kilograms. Okay, so let's just kind of write that down off to the side, see if we need it. I didn't mention anything about mass up above, so might really not need it. And a diameter of 2.4 meters. One person pulls clockwise, so we have the clockwise person here pulling with 43 newtons, and the other person is pulling counterclockwise at 67 newtons. Okay, what is the net torque? We're looking for net torque on the wheel. Okay, so let's write our torque equation down again. So that's the Greek letter tau. That's what we use for torque in physics. So it's force times radius. And so I just said radius here, or lever arm. So in the case of something that is circular, so this is a pulley here, or we could have a wheel or something like that. In the case of something that's circular, we're pulling around the outside edge, we need a radius. So our diameter is 2.4 meters. To get a radius, we cut that in half, because a radius would be to the center of the circle. So that's going to be 1.2 meters for our radius. Okay, well that's going to give us that piece there. So what we want to do, we want to find the torque of this person pulling and the torque of that person pulling, and then we can put those two torques together to find the net torque in the system. So let's just call this the left side. So we're going to find the torque on the left side, and then let's call that one the right side. So we're going to find the torque on the right side. So our torque on the left side, we're pulling with 67 newtons. Okay. And then again, since it's force times radius, we're pulling on this pulley here with a radius that has a radius of 1.2 meters. All right, we'll get that number in a second. And then our right side, we have 43 newtons. And that again is 1.2 meters for the radius. So let's get these two numbers. All right, so 67 times 1.2. That's going to give us a torque of 80.4. Okay, and the label for torque, we can pay attention to the labels that we used here. The standard, or SI, would be Newton times meter. So 80.4 Newton meters. Okay, so let's get our second one here. So 43 times 1.2. That's going to give me 51.6 Newton meters. Okay. Another label for torque in the English or American units is pound-foot or foot-pounds. I think we write it as pound-foot, but we can say foot-pounds. Foot-pounds kind of rolls off your tongue a little bit better, but we're not using those here. We're using Newton meters. Okay, so let's talk about these numbers here and what we do to get the net torque here. Okay, so net torque would be the torque on the left and the torque on the right. We have to talk about which one's positive and which one's negative. So in order to figure that out, we kind of think of the unit circle. So we could think of this as our unit circle, if we have measurements that are going this way, which would be below the horizontal, that's going to be negative. So this would be a negative angle, which would produce a negative torque. Okay, so that's the 43 newtons, that's the right, so that one's negative. So clockwise torque is always negative. So those clockwise motions are always going to be negative. Counterclockwise would be positive because that's going to be up from the axis. So that would be like going from 0 to 90. That's a positive angle, so it's a positive torque. So this is a positive 80.4 newtons. So to get the net torque, we're going to just add those two together, which would be 80.4, and that's going to be minus or plus a negative. So 80.4 minus 51.6, and that will give us 28.8. Okay, so 28.8 Newton meters. That is the net torque. So we can kind of think about how this is going to work. We have the person pulling on the left with 67 newtons, the person pulling on the right with 43 newtons. Obviously, we know the pulley is going to rotate that way, or the person pulling with more force will win, right? But now we turn it into a torque unit, so the person on the left will generate more torque than the person on the right, and the net torque on that wheel will be 28.8 Newton meters. So it's going to be going in a counterclockwise with a torque of 28.8 Newton meters. Okay, let's look at another one down here. So we have two people sitting on a seesaw. Okay, and we want to figure out where that rotation point should be, where that fulcrum should be for that seesaw. Okay, so we have one person, 56 kilograms, another person, 43 kilograms, and they want to balance on that 1.75 meter long seesaw. Okay, so now we don't have any forces involved. Okay, so forget about that little subscript there. Let's say we got the force of the person on the left and the force of the person on the right. Okay, if we wanted to make a different subscript, it'd be F sub F for force of Felicia. And then the one on the right would be force of Araya, so F sub A. Now we have to kind of think back to some basic physics stuff here, basic physics concepts. If we have 56 kilograms, how do we turn a mass, so that's a mass measurement, how do we turn a mass measurement into a force? Well, what's always pulling down on the mass here? Well, that's gravity, which is 9.8 meters per second squared. So let's figure out the force of Felicia. We'll make the capital F. So that's going to be her mass, 56 kilograms, times the pull of gravity, which is 9.8 meters per second squared. Alright, so we'll have to multiply those two to get that value, and that ends up giving us 548.8. And the forces are measured in newtons here. Okay, so now let's do the force of Araya. Okay, and the reason we're doing forces here, because remember torque is going to be force times the radius, and in the problem we're really trying to find the radius of the left and the radius of the right to figure out where that fulcrum is going to be. So we have 43 kilograms times 9.8 meters per second squared. That's going to be 43 times 9.8, so 421.4 newtons. Now, if these two individuals were balanced on here, let's say that this were in the center, right? So if this is in the center, then they are not going to be balanced. Right now, we're going to kind of assume that they're balanced, and we need to figure out where that's sitting. So if this were in the middle, then we would have to calculate the force or the torque of the person on the left and the torque of the person on the right if we wanted to do anything with the radius or the radii. Okay, so now how do we figure this out? We don't have a radius given to us here, nor do we have a radius given to us here. Okay, so this is the radius of Felicia and the radius of Araya there. We are given that the whole length of the seesaw is 1.75 meters. So can we say this? So we can say the radius of Felicia plus the radius of Araya is going to be equal to that 1.75 meter long seesaw. Right, that makes sense because we have the radius of the two individuals. That's going to equal the total length of that seesaw. So this is kind of the trick of this problem. We have to have this in order to find where that's going to be. So let's kind of do like we did on the last one where we say torque on the left and torque on the right. So we're saying that this is a balanced system because we're just trying to find that point for the balanced system. So we're going to have the force of Felicia on the left times the radius of Felicia. Okay, because this is just in general the torque equation, force times radius. And then we're going to have the force of Araya on the right times the radius of Araya. And now we need to plug some stuff in. So we found a force up there, so 548.8 newtons. We don't know that radius yet. We found a force of Araya, so that's 421.4 newtons. And we don't know her radius either. So how do we get that? Well, we have two unknowns in this equation here. We also have two unknowns here. So with a little bit of algebra, we can find it. So let's rearrange this. So let's solve for this variable here. So let's solve for the radius of Felicia. So in order to do that, we're going to have to move this over. Okay, so move that r sub a over, and we're going to have 1.75 meters minus r sub a. So now, what can we do? We solved this. Now we can do a little bit of substitution because this is equal to that, and we have r sub f there. So we can plug that in. So let's do so. So 548.8 newtons times, let's plug in this stuff here, 1.75 meters minus r sub a equals 421.4 newtons times r sub a. And now there's just one unknown here that we can solve. So let's keep rolling with this one. So this would distribute into there. So 548.8 times 1.75. Okay. So that would go into there. I like to do this when I distribute stuff just so I know I'm going to both of them. So that gives me 960.4. And we can maintain units here if you want to. In the end, we're looking for a radius. That's going to be in meters. Okay, so just, I'm going to forget about my units here so I don't have to write them as many times. So 960.4 minus 548.8 r sub a equal 421.4 r sub a. So now we're going to move this over. Okay, so this is some basic algebra here. R sub a, so add those, so these will go away here, and we'll have 960.4 is equal to, so let me get that number here, 421.4 plus that, 970.2. And that's r sub a. All right, so now how do we get rid of this? We're going to have to divide that. And then we will be left with our answer. So r sub a is going to be, so 960.4 divided by 970.2. And then we get 0.99. So 0.99, and that, again, since we found a radius, that's going to be in meters. Okay, so that's one of them. Okay, so how do we find the other one? Well, we have this radius here. We can take it and plug it into there because we found r sub a, right? So we're going to do 1.75 minus 0.99. And we get 0.76. So that's the radius of Felicia. We get 0.76 meters. Okay. So we have those two radii, so 0.99 meters and 0.76 meters. So that tells us that we are 0.76 meters in from the left and 0.99 meters in from the right. Those two radii would produce a balanced system, or a system that's in equilibrium. So these are the answers here. All right, so that problem was a little bit more complicated than a normal torque problem like this one, but hopefully that helps you figure out problems with torque and equilibrium. Thank you.